This is the semester test part 2 review. Just to remind you, the semester test part 1 and 2 must be completed on Tuesday, January 14th, and I will have a classroom open from 12 to 2 p.m. on the 14th if you'd like to complete your test at that time and ask me for guidance on questions. A link for that class is going to be provided in your OLS. Also, just FYI, Part 1 has 15 questions. The test is worth 75 points. Part 2 is 5 questions. It's worth 52 points. Now, as far as the grades are concerned, your semester final test is 12% of your final grade, just so you know. Okay, now the questions that I've provided in this review are similar to the questions that you're going to find on your test. So just pay close attention. Coordinate geometry. Determine whether parallelogram ABCD is a rhombus, a rectangle, or a square, and list all that apply. And explain your answer. Now, explaining it means you got to give me some verbiage, words, like you're in English. Okay, they give us the coordinates. So what do we do first? Well, I bet you're thinking, let's go ahead and plot those coordinates. Plot the points. So there's our points. I'm going to go ahead and label them with the letters they've given us. And I don't think, what do I do after connecting the points? I didn't think I had a connectors in there, so let me go ahead and add that. Let me get my pen. Let me go ahead and connect my points. Not very straight lines, but they'll do. Oh, that one was way off. There we go. Alright, it says, what do we see after we connect the points? Well, we definitely know we have a quadrilateral, okay? And it kind of looks like a square, but we can't make any promises. I'm just going to erase this extra line I got out there because it keeps bothering me. Okay, looks like we could have a square, definitely a rectangle. I don't think it's just a regular parallelogram. Oh, a rhombus. I didn't think of a rhombus. So what are the properties of a rectangle, a rhombus, and a square? Well, remember they share all the same properties of a parallelogram, okay? But rectangles also have diagonals that are congruent, and of course it's all right angles. A rhombus has diagonals that are perpendicular and bisect the opposite angles. And a square has the properties of a rectangle and a rhombus, plus all that of a parallelogram. So it looks like my key thing that I'm going to be looking for here is the fact that diagonals are congruent, diagonals are perpendicular. That's going to help me figure out, is it a rectangle, a rhombus, or a square? Okay, so now we got to remember, how are we going to prove that the lines are perpendicular? Okay, well, we know that we can calculate the slopes of adjacent lines. The slopes of perpendicular lines are going to be reciprocals, okay? Therefore, the parallelogram is going to be a rectangle or a square, okay? The sides of a rhombus are not perpendicular. Their diagonals are, okay, but not the sides. So if I go through here and say I calculate the slope of AB, AD, and CD, and if I find out they're all perpendicular, then I know I've got a square or a rectangle. So what would I want to prove next to determine if the parallelogram is a rectangle or a square? I would want to compare the lengths of the sides using the distance formula or the Pythagorean theorem, or calculate the slopes of the diagonals. Okay, so all of that got us prepared for this. It's the same problem, I just don't have the graph anymore. Okay, and I'm going to show you an example of what your problem should look like. First, remember, let me go back and look at that slide. I got to remember how my points laid out. A, B, C, D. Okay. So I'm just going, I can't do it with a highlighter. So I'm going to put B, A, C, D. Okay. Oh, there I just drew it. It looks like a rectangle. Okay. So that's just so I know where my points are. First, I'm going to say, let's look at my sides. I'm going to do the slope of AB. So my slope, you remember you do x1, y1, x2, y2. So I'm going to have the y's on top, 1 minus 3. The x's, negative 3 minus 1. So I'm going to have a negative 2 over a negative 4, which equals a positive half. Okay, now I'm going to calculate, I'm going to put here slope equals a positive 1/2. So for AD, I'm going to put negative 1 minus 3 over 3 minus 1, so I get negative 4 over 2, which gives me a negative 2 over 1. So those are opposite reciprocals. Okay, so that tells me those guys right there are perpendicular. Now I only have to do one more side. So let's do BC. So I'm just going to put x and y. So I have negative 3 minus 1 over negative 1 minus a negative 3. So that gives me a negative 4 over 2, which gives me negative 2 over 1. So that means my slope over here is also a negative 2. So I'm definitely dealing with some perpendicular segments. Therefore, I know that it's a rectangle or a square. It's not a rhombus. So what I'm going to do now is my next step, let's look. It says, what do I want to prove next? I want to compare the lengths of the sides using the distance formula or Pythagorean theorem, or calculate the slopes of the rectangles. Okay, now remember, the diagonals. Remember, the diagonals of a square are perpendicular, but they're not perpendicular with a rectangle. So I'm going to go ahead and do that. I'm going to compare slopes of the diagonals. Okay, so my first diagonal is AC that I'm going to check out. So I've got negative 3 minus 3 over negative 1 minus 1. Oops, almost put the wrong answer down there. So I got negative 6 over negative 2, which reduces to a positive 3 over 1, or just 3. Okay, my slope for BD is going to be negative 1 minus 1 over 3 minus a negative 3, which gives me a negative 2. These two guys become positive, so that's a 6. So I get a negative 1/3. So these guys right here are opposite reciprocals. So now I know, and it doesn't look that way in the picture, that those are perpendicular. So my final answer is I'm dealing with a square. Okay, that right there is a coordinate proof. And I believe y'all had a problem like that on your Unit 5 test. And that's what you need to do to prove those. Now I could have also went in and seen if all three of those sides had the same length, but that was going to take more work. And I don't like doing a lot of work. Okay, now you're going to have a couple of proofs on your test. And the first thing is when we're talking about a review of proofs, I just wanted to remind y'all of how we go about following the process. And one of the best examples that I have found is that having to be around a little kid or a small child. They're always asking why, for everything. Every answer you give, they ask another why. So you end up having to justify everything you say. Well, that's what we do with proofs. Now here I said that geometry proofs aren't much different, and however they do come to an end, unlike the little kid questions. It says think of a proof as a big puzzle and you have rules that must be followed to put it together. The more rules you know, the better at solving the puzzles you are. You've learned lots of rules so far in this semester, and like definitions, properties, postulates, and theorems. What makes definitions special is that their converses are always true. Not so with postulates and theorems. It just works with definitions. And here's an example. It says angle bisector is a ray that divides an angle into two equal parts. So if I look at this, it says if a ray divides an angle into two equal parts, then it is an angle bisector of that angle. This is what the converse looks like. Remember, converse is where I'm flipping the hypothesis and the conclusion. It says if a ray is an angle bisector of that angle, then it divides an angle into two equal parts. Since both of those are true, then that is a good definition of an angle bisector. Now, what we need to remember about rules, they can all be written in if-then form, which means they can all be used in proofs. Okay, because your reasons you need to be able to write them in an if-then form. Okay, so, and if you remember back from when in Unit 2 we went through this, and I'm just going back over it again. This is a very, very simple proof, and it doesn't even have to do with math. The rules are, if Lydia wears purple, then Claudia wears purple. If Claudia wears purple, then Patty wears purple. If Patty wears purple, then Joni wears purple. Now then, our given states if Lydia wears purple, okay, that's what our given is, and we have to prove that Joni wears purple. So my first statement says Lydia wears purple, and oops, I didn't want to write on it. And then the second column says, but why? How do we know she wears purple? Well, it's given to us right here in our given. So I'm going to put given there. Given is almost always your first statement. The second statement said Claudia wears purple. Well, it says, why can we be so bold and say that? And the reason is because we have this rule up here, and that rule says if Lydia wears purple, then Claudia wears purple. And so that's what I put down here for my reason. The third one says Patty wears purple. So how do we know that Patty wears purple? Well, we've got this other rule that says if Claudia wears purple, I'm not writing this all out. Maybe I'm not even writing the word if. But if Claudia wears purple, then Patty wears purple. Okay? And the next one says, well, Joni wears purple. And you say, well, I know that's true, because if Patty wears purple, then Joni wears purple, because that's what that rule tells us. Oop. Okay, so here's a neater way to look at it. Look here, it says Lydia wears purple was given, Claudia wears purple. Now notice how in my reason, my phrase following the if matches my previous statement. And then the phrase that follows then matches my current statement. Okay? And then it works out the same way for the third step of the proof of Patty wearing purple. It says if Claudia wears purple, then Patty wears purple. Well, notice the phrase following the if matches my second statement. Now it could match the first, but in this particular proof it matches the second one. Then Patty wears purple. Your phrase following the word then is always your current statement. So this one, it always matches your current statement. This could be any previous statement. It just depends on where you want to go with your proof. And then the last one, Joni wears purple. So, and that matches Patty wears purple, and then the current statement, Joni wears purple. Okay, so here's another one. It says given angle 1 is congruent to angle 3. So let's prove that angle 2 is also congruent to angle 3. Well, our first statement says angle 1 is congruent to angle 3. And then, but look at this, it also says angle 1 and angle 2 are vertical angles. Well, how do we know that? Well, we've got up here that angle 1 is congruent to angle 3 is given. If you look over here at the figure, one thing you can assume when you see a figure like this, these are vertical angles, and vertical angles are always congruent. So we can say that that is also a given. Okay. The next statement says angle 1 is congruent to angle 2. Well, what rule that we've learned guarantees that? Well, we learned, I believe it was in Unit 1, that vertical angles or we learned the vertical angles theorem, which states that vertical angles are always congruent. Now, if I was going to write that out as an if-then statement, I would have said if angle 1 and angle 2 are vertical angles, then angle 1 is congruent to angle 2. So, therefore, angle 2 is congruent to angle 3. Well, how do we know that? That comes from the rule that we also learned called the transitive property. And that's going to be the end of this proof because I've proved what they've asked for. Now, what I did on this next slide was I showed you how the if-then works in the proof. And I kind of already told you about the second reason. It says if two angles are vertical, then the angles are congruent. Well, you can look at at the transitive property in reason 3, and it says if angle 1 is congruent to angle 3, and angle 1 is congruent to angle 2, and see how I pulled those from the statements 1 and 2? Okay, then angle 2 is congruent to angle 3. I wanted to tell you right quick, you can also go back and watch the reviews in Unit 2 for the test, and that'll also help you prepare for the final. I sent it to you in the CC recording, the same properties of equality, so that way you could copy the whiteboard. I believe there's also a copy of it with your postulates and theorems in doc sharing. So what can you assume in a figure when you look at it? Because I'm always telling you, oh, you can't assume that. Oh, but you can assume this. So let's just get us a list going. What you can assume. That lines and angles that look straight, they really are straight. They're not trying to fool you with that one. If two lines seem to intersect, they really do. So if lines are intersecting, you can assume you got some vertical angles going. If points look collinear, they really are. And remember, collinear means you've got several points, at least two, that are all on one line. That's what collinear means. So if they look collinear, they really are. Betweenness. If a point is on a line and it seems to be between two other points on a line, it really is. Okay? It's not really on the right side or on the left side. It's really in between them. Relative position of points. If a point looks like it's to the right of another point on a line, it really is to the right. Okay, they're not trying to fool you. If angles look like vertical angles, they really are vertical, and therefore they are congruent to each other, because all we need is two straight lines that intersect to create vertical angles. Now, what you cannot assume in a figure, just because an angle looks like a right angle does not mean it is. Okay, so never assume it's a right angle unless the picture tells you so. Just because two segments or an angle look congruent does not mean that they're congruent. Just because one segment or angle looks bigger than another one does not mean it is. You got to do the math. Just because two lines look parallel or perpendicular does not mean that they are. Just because one segment or angle looks bigger than another does not mean that it is. And there are tons more things we can't assume from looking at a figure. These are just some very common ones. But basically, if it isn't on the assume list, then don't assume it. So, figures and givens plus rules will lead you to a conclusion. And if a figure is not given, then you need to draw it. The reasons answer the but why. For each reason, you will write given or an if-then rule. And a lot of times we abbreviate the if-then rule, like with vertical angles theorem or reflection property or transitive property. But those are just abbreviations for the if-then statement. And also remember, your reason may not always look like if-then. Sometimes you have to write definition of congruent or property of addition or segment addition postulate. To determine if the ifs match previous statement and thens match the current statement, you have to do so by writing the rules out or visualize them in your noggin. So go through problem sets and practice completing the proofs with the statements completed for you, and then check your answer with the answer key. And this is one of those things, practice makes perfect for writing good reasons. Now let's look at conditional statements. This one says, I am a skunk, so I stink. That's just a statement. So write the statement in if-then form. You write, if I am a skunk, then I stink. The hypothesis is I am a skunk because it follows the word if. Your conclusion is I stink because it follows the word then. If a correct formal proof of this statement is given, is the reason being used inductive or deductive? Well, it's going to be deductive, okay? Because if you're with a skunk and he sprays, you know he stinks. It's proof. How is the answer in the last question different from other type of reasoning mentioned? Well, inductive is reasoning from specific to general, and deductive is reasoning from general to specific. And we had some examples of that in the Part 1 review. You need to know transformations and their rules, and I went through this pretty clearly in the Part 1 review. You will be expected to graph transformations and include them in your completed test. These are just some of the rules that you go by. So for the semester test Part 2, 1 and 2 must be completed on January 14th, and again I'm going to have a classroom open from 12 to 2 on Tuesday, so you're welcome to come in there and work on your Part 1 and or your Part 2 and just ask me questions for guidance. And that's going to be it. Thanks for listening to your Part 2 review.